Hello and welcome to this online video lecture about enthalpy and entropy. By the end of this video lecture, you should be able to define both of these terms. You should understand what they mean thermochemistry-wise, and then you should be able to identify situations where one or the other or both of them is increasing or decreasing. We're going to start with the definitions. We've actually been learning quite a bit about enthalpy in this course, and I probably have said it in a few lectures already. Or I probably just have not formally introduced it, but enthalpy is basically what we refer to in chemistry as heat energy. So when we talk about how much heat or heat energy something has, that's its enthalpy. And as we've learned before, when it comes to heat, um, how much, there's two things that matter. The average kinetic energy of the particles in the matter of the system that we're talking about, and the number, the quantity of particles in the system that we're talking about, because heat is like the sum of all of the kinetic energy. Heat is the total of all the kinetic energy that those particles have. And so that heat energy that we've been talking about this whole time, the formal term for that is enthalpy. And so then we have this other weird term that I don't think I've talked about at all yet, and it's called entropy. And this is a vocabulary word that we use to describe the amount of randomness or chaos in a system. So this one's a little bit harder to understand. It's a little bit more foreign, I think. But if a really good analogy that I like to use is like your bedroom. So, you know, when you clean your bedroom, you're putting everything in its place. It looks like an N. There we go. You're cleaning your bedroom. You're putting everything in its place. You're ordering your bedroom. You're taking something that was very random, like clothes that had just fallen like wherever, or empty food containers that you just kind of left wherever you were done eating. You're taking those things that were just randomly scattered about your room, and you're putting them in order. You're putting them where they belong, and it takes work to do that. You have to expend energy in order to do that. So what you're basically doing is you are using energy to do work that then decreases the entropy of your room. And an interesting thing about the universe is that the universe tends to, whenever something happens, the total entropy in the universe has to go down. I'm sorry, no, I just totally blew it there. The total entropy of the universe has to increase. The randomness in the universe is always constantly increasing. And if you want to take a little pocket of the universe, if you want to take like a little bit of the universe, a tiny little system somewhere like your room, and you want to decrease the entropy, then you have to put work, do some work. You have to put some energy into the system and do some work on it in order to make that happen. So entropy is randomness or chaos or disorganization, and it's different from enthalpy, which is basically heat energy, but they are related to each other. So let's take a look here at some examples of then how you can tell if one's going up or not, or the other's going up or down, or all this good happy fun stuff. Let's say you have a bathtub. I think I've used this example before. So you've got a bathtub, and you start filling the bathtub up with water, and you carefully control the bathtub so that the water that you put into it is, I don't know, let's pick a temperature. Let's say it's 25 degrees Celsius. All right, and then you stop. There's a certain amount of enthalpy in the bathtub at that point. Because if you took all of the kinetic energy of every single water molecule that you put into the bathtub, and they all have a specific, very close to the same amount of kinetic energy, because the average of their kinetic energy gives us this temperature called 25 degrees Celsius. But if you took all of their kinetic energy and you added it up, that would be the enthalpy of the water that's in there. Now, let's say then that we very carefully added some more 25-degree water to the bathtub out of the faucet. I don't know, that's kind of a weird spot for the faucet to be. So we open up the faucet, right, and we add some more 25 degrees Celsius water into the bathtub. Now, an interesting thing happens. The temperature of the water in the bathtub doesn't change because temperature is an average of the kinetic energy of the particles. However, the enthalpy of the water in the bathtub does change because remember, enthalpy is the sum. So because you're adding more water molecules and each of those water molecules has, that same average kinetic energy, since you're having more water molecules now, there's more heat energy, so there's more enthalpy. So if you add water to a bathtub like that, then the enthalpy would go up. Now, when you think about the entropy inside of this bathtub, imagine what you have. You've got water molecules, and they're not really locked in place. They're kind of touching, but they're all just kind of randomly, chaotically moving around in here, just all over the place. We're water molecules. When you add more water to that, you don't really change what's going on inside of there. They're still kind of moving around in the same random, chaotic way. They don't become more or less disorganized. So the entropy of that water, when you add more of it, doesn't really change at all. So adding, no change, not change. So adding more water of the same temperature to a bath is an example where the enthalpy of the system goes up, but the entropy of the system doesn't change. Let's see if I can maybe come up with a different example here. Okay, let's say that I've used this example before too, but let's say you have a sitting out on a counter, you have dropped an ice cube. And I go back to water a lot because it's something that you guys are pretty familiar with in your everyday lives. So it's a good example to use. I feel like it's fairly understandable. Okay, good. So as the ice cube sits out on the counter, the energy from the air in the counter, the heat energy, start to go into the ice cube. And at first that doesn't change the temperature of this ice cube. What it does is it starts to transition the molecules from being solid, which means that the molecules are locked in place, orderly arranged, locked in place, and just kind of vibrating, right? To being a liquid, which we would call melting. And so let's say we get like a little puddle of water starting to form here on there. Okay, now in the liquid, like we talked about just a few seconds ago with the bathtub, the water molecules are all just kind of randomly moving around and sliding past each other and kind of bouncing and wiggling all over the place. So in the solid ice cube, they're arranged, orderly, and locked in place. But out here in the liquid, they're just kind of randomly rolling past each other. So that means that the liquid water has a higher entropy than in the solid water. So when something melts, its entropy goes up. And the temperature may not necessarily be any different because all of the energy that's coming in from the outside is going to just changing it from solid to a liquid. Now, after it becomes a liquid, as the liquid absorbs heat energy from the air in the counter, then its temperature is going to go up and these little particles are going to start to move faster. So just melting doesn't increase enthalpy, but after the water melts and it sits out on the counter and starts to absorb energy from its surroundings, then its enthalpy will start to go up because those water molecules will start to move a little bit faster. So melting itself, like the instant of melting, there's really no enthalpy change there, but after it melts, and then you have that new state, whether it's liquid or, well, if it's melting, it would be liquid. When you have that liquid sitting on your counter, it absorbs energy, heat energy from its surroundings, and then its enthalpy might start to go up. Another thing is that more and more of this ice cube melts, you're going to get more and more liquid molecules. And since enthalpy is the sum, as you get more liquid molecules as the melting proceeds, even if their temperature, if the average kinetic energy is the same, you have more of them. So that also makes the enthalpy of the puddle of water that the ice is turning into go up. And as you can imagine, if it sits here long enough, some of these water molecules are going to evaporate. They're going to become even more random as a gas. They're going to be zinging all over the place in random straight lines until they hit something, the water molecules. And so that's even higher entropy as a gas. So solids have the lowest entropy, and then liquids and then gases have the highest. And so, when you have changes of state, if you keep that in mind, then you can kind of predict whether the entropy is going up or down depending on how the state is changing. So that's just a really quick kind of primer on enthalpy and entropy and kind kind of how you can figure out whether they're going up or they're going down. Make sure you can define these two terms. Make sure you kind of understand how they work with everyday common situations. That's what your quiz is going to be over. And as always, if you have any questions, feel free to ask in class.